Hey everybody, welcome back to another AP Precalculus video. Today we're going to be going over 1.5 polynomial functions and complex zeros, part 2. So this is the second part to our 1.5 videos. The first video will be in the description box below if you want to check that out. But today we're going to be going over the rest of the topics that we didn't go over last video. So we're going to be finding the degree of a polynomial based on given tables. And then we're going to be looking at even and odd functions. These are all the learning objectives for Unit 1.5 if you want to pause and take a look at them. So our first topic is finding the degree of a polynomial. Now, the way you can do this is by looking at successive differences of outputs between equal length input value intervals. So that's just looking at the differences between our outputs over their corresponding input values, which are evenly spaced apart. So the first difference is going to be constant if the polynomial function has a degree of 1. Again, degree is just the largest value in which x is raised to. So first differences being constant means that the degree is 1. Second differences being constant means that the degree is 2. Third differences means that the degree is 3. And this relationship applies moving forward. So for the fourth differences means degree is 4. Fifth differences means the degree is 5, and so on. So here's what we mean by first difference, second difference, etc. Right here, we're given f of x's output values and corresponding input values. So first differences is just the differences between our successive output values. So we have 0, 1, 2, 9, 28. So just the differences between each. So 0 minus 1 would be negative 1. 1 minus 2 would be negative 1. 2 minus 9, negative 7. 9 minus 28 equals negative 19. And of course, our input values are equal length input value intervals. That just means that they are equally spaced apart. So negative 1, 0, 1 unit apart, 0, 1, 1 unit apart, 1, 2, 1 unit apart, 2, 3, 1 unit apart. So we're taking these output values of these equally spaced inputs. So first differences are not constant. We have negative 1, negative 1, negative 7, negative 19. They're not the same. So that means that our degree cannot be 1 because functions with a degree of 1 have constant first differences. So now we're going to be looking at our second difference, which is basically just the difference between our first differences. So we're going to take these values right here, and we're going to subtract them from one another, successively, of course. So negative 1 minus negative 1, negative 1 minus negative 7, negative 7 minus negative 19. So if you look over here, you can see that we did the math, and our second differences will be 0, 6, and 12, which again are not constant. Now, constant second differences mean that our degree has a function of 2, but since these are not constant, there's no degree of 2. So then we're going to be looking at third differences, which is the difference between our second difference. So hopefully you're noticing this pattern here, what first difference, second difference, third difference means. Now looking at our third difference, we're going to be finding the difference between our second differences, 0, 6, 12. So 0 minus 6 is negative 6, and 6 minus 12 is also negative 6. And since negative 6 is our constant third difference, negative 6 equals negative 6, that means that our polynomial function f of x has a degree of 3. That also means that it is cubic. That's how you use differences to find the degree of a polynomial function from a given table. Next, we have even and odd functions. Now, a function is even if f of x, let's say f of x is our function, f of x equals f of negative x. This also means that it is symmetrical about the y-axis. And a function is odd if negative f of x equals f of negative x. And that also means that the function is symmetrical about the origin. So we're going to take a look at some graphs for that to make sense. Right here, g of x is going to be even because g of x equals g of negative x. So let's take a look at x equals 2. So for x equals 2, that means g of 2 is going to be 0.6. Right there is 0.6. And let's take a look at g of negative x. Well, if x equals 2, negative x is just negative 2. So g of negative 2 is also going to be 0.6. So since g of x equals g of negative x, g of 2 equals g of negative 2 equals 0.6, that means g of x is symmetrical about the y-axis and is therefore even. Here's what we mean by symmetrical across the y-axis. If you flip the function across the y-axis, if it is even, it will look the same. So let's choose a different color. Okay, so I'm going to demonstrate that and trace this function. It won't be perfect, but hopefully we get the idea. Okay, so if we took what we just traced, our even function, and we flipped it horizontally, we flipped it across the y-axis, you can see that it looks the same. So that's what we mean by symmetrical about the y-axis. You can flip it and it'll overlap. Next, we have r of x, which is odd, and here's why. Negative r of x will equal r of negative x because r of x is even. So let's take a look at x equals 1. So if x equals 1, we're going to look at r of 1. R of 1 is equal to 1. Now, right here, we want negative r of x. Well, negative r of 1 is just going to be negative 1, since r of 1 is 1. All right, so now let's look at r of negative x. Well, if x equals 1, negative x is just negative 1. So let's look at negative 1, which is equal to negative 1. R of negative x, r of negative 1 is going to be negative 1. So since both negative r of 1 and r of negative 1 equals negative 1, it follows this relationship right here. That means that the function is symmetrical about the origin, and therefore r of x is odd. All right, now here's what we mean when we say that it will be symmetrical about the origin if the function is odd. So we have our odd function from earlier. And if we traced it like so, and it might turn out a little bit wonky because I'm not tracing it perfectly, but it should be roughly about the same. And flipping it, we're just going to flip it horizontally and then vertically. And as you can see, it's the same function. Our values are all the same if you flip it about the origin like that. So that just means that the function is odd. So that's what we mean when we say symmetrical about the origin. All right, we're going to be moving on to some examples now. We're going to be looking at 4 examples in this video. First, we're going to be finding the degree from tables. Right here, we're given h of x's output values and corresponding input values, and we're going to see what the degree of x is. So we're going to be looking for those differences between these successive output values. All right, so first we're going to be taking a look at those first differences. So we're just going to directly take these output values and subtract them from one another. So 401 minus 1,601, 1,601 minus 3,601, 3,601 minus 6,401, and 6,401 minus 10,001. So these outcomes are going to be our first differences. Now you can see that we're getting different numbers, which means that first differences are not constant. Therefore, the degree is not going to be 1. So we're going to keep going and see if other differences will be constant. Now we're going to take the differences of the first differences to find our second differences. So negative 1,200 minus negative 2,000, negative 2,000 minus negative 2,800, and then negative 2,800 minus negative 3,600. And as we can see, we're getting 800 for all these differences, which means second differences are constant, and therefore h of x has a degree of 2, and that also means h of x is quadratic. All right, next we have example 2, which is a multiple choice question, and we're going to be looking at the degrees of these tables. An unknown function has a degree of 1. Which functions, according to the given tables, could potentially be the unknown function? Select all that apply. So we're going to be looking for those first differences, and we're going to be wanting those first differences to be constant. That's how you get a degree of 1. So we're going to look at the tables one at a time. Option A is g of x. So we're going to take these output values and find the differences between them. So 37 minus 205 is negative 168. 205 minus 877, negative 672. 877 minus 1,381 is negative 54. And then 1,381 minus 1,997 is negative 616. So since these first differences are not constant, that means g of x cannot have a degree of 1. Therefore, a is not an option because we're looking for a function that has a degree of 1 based on these given tables. All right, we're going to look at b now. M of x, we're going to find the first differences, 3 minus 5, 5 minus 7, 7 minus 9, 9 minus 11. Now, they're all equal to negative 2, so you might think that the first differences are constant, and technically they are, but we want to pay attention to our input values as well, because we want them to be equally spaced apart, equal length input value intervals. That's how this would be reliable. So 1 and 3 is 2, 3 and 7 is 4, 7 and 12 would be 5, and then 12 and 19 would be 7. Since our input values aren't equally spaced apart, even though these first differences are constant, they're not constant over equal length input value intervals. Therefore, m of x doesn't have a degree of 1, which means b is also not an option. So we want to be careful of our input values as well. We want to make sure they're over these equal length input value intervals. That's how our first difference, second difference method would be reliable. All right, now we're going to look at option C. We have s of x. So 12 minus 14, 14 minus 16, 16 minus 18, and 18 minus 20. And that's all equal to negative 2. And if we look at x over here, we do have equal length input value intervals. They're each 10 units apart, which means that this function is linear and it has a degree of 1. So C is an option. All right, lastly, we have option D. So J is a constant, so keep that in mind. But we're just going to treat it the same as all the other tables. So K of x, we're going to find the first differences, 17j minus 9j, 9j minus j, j minus negative 7j, and negative 7j minus negative 15j. And again, our input values are equally spaced. So because these first differences are constant, that means K of x will have a degree of 1, which means D is also an option. So out of these 4 options, only C and D are could possibly be the unknown function because they have a degree of 1. All right, next we're going to be looking at even and odd functions. So we're going to be looking for those relationships for even and odd functions. Now, if g of x was even, the relationship would be g of x equals g of negative x, all right? So we're taking the opposite of those input values. So let's test that out. Let's say x is 1. If g of 1 is 4, g of negative 1 should also be 4. So let's take a look at g of negative 1. Yep, g of negative 1 is 4. So that means that g of x is even. And we can also tell because it is symmetrical about the y-axis. If you flip this graph across the y-axis, you would have the same graph. All right, we're given u of x, and we want to know if u of x is even or odd, and then we're going to talk about y. So let's just look at those relationships again. If u of x is even, u of x would be equal to u of negative x. So let's take a look at x equals 1. So u of 1 is 1. And that would mean if it was even, u of negative 1 has to also equal 1. So u of negative 1 is equal to negative 1. 1 isn't equal to negative 1. So u of 1 is not equal to u of negative 1. Therefore, u of x is not even. Now let's see if u of x is odd. So for odd functions, negative u of x should be equal to u of negative x. So again, let's look at x equals 1. Negative u of 1, well, u of 1 is 1, so negative of that is just negative 1. And then u of negative x, so u of negative 1 would be negative 1. So since they're both equal to negative 1, u of x is an odd function, and that means it's symmetrical about the origin. All right, that is everything for Unit 1.5, Polynomial Functions and Non-Real Zeros, Part 2. Again, Part 1 will be in the description box below, so you can check out the rest of our topics from Unit 1.5 if they weren't talked about in this video. Thank you so much for watching, and stay tuned for more math help. Bye!